Greetings and namaskar to each one who came here to watch this video.
In this video, we are going to grab knowledge of Gauss Law and we will see its proof. Additionally, we will study its differential form. So let's start. Gauss Law. It deals with the closed surface and the main thing under Gauss Law is electric flux. Alright? So mathematically, we write Gauss Law as this is closed line integral. Why it is closed? Because it deals with the closed surface. So we have taken closed line integral. Here E is the electric field that are passing through area ds. So E dot ds shows the flux and it is equals to Q enclosed divided by epsilon naught. Here Q enclosed is the total charge present in this closed surface. Means it is the sum of all the charges inside this enclosed surface. Okay? And epsilon naught is the permittivity of free space. And if we take vacuum, then we will use only epsilon. What is permittivity? It is basically the capacity of the substance to permit or to allow the electric fields to pass through them. So, flux, that is E dot ds, is equals to the total charge divided by epsilon naught. So, that net outward electric flux through a closed surface is equal to the sum of the charges inside the enclosed volume divided by the permittivity of the free space. Here, such a hypothetical closed surface is known as Gaussian surface. So, the easiest way to calculate the electric field is through the Gauss law. Now, coming to the three important points of electric flux. Number 1. Electric flux, that is E dot ds, is independent of the size and shape of the Gaussian surface as long as Q enclosed is same. What does it say? Suppose we have any Gaussian surface having Qn charges. So it will produce electric flux, that is E dot ds. So this is saying that electric flux is independent of the size. Means the electric flux will not depend on the size. It may be this or any irregular size, may be small or may be big. So electric flux will not depend on the size and the shape because electric flux depends on the charge, the amount of charge present. So it will produce electric field according to the charge. So size and shape doesn't matter. Number 2. So the second point is electric flux doesn't depend on the location of the charge inside the closed surface S, whereas electric field at each point on the surface S is dependent on the location of the charge. Here we are talking about the location. So suppose we have a point charge Q here. So no matter whether we have charge here or at this point or at this point, it will produce the same amount of the electric flux. Means electric flux doesn't depend on the position of the charge. But electric field depends, because if we have charge here, then the intensity of the electric field will be maximum over here, and if we have charge here, then electric field intensity would be maximum over here. So flux is independent of the location. So number 3, electric flux is unaltered by the charge outside the closed surface S, but outside charge contributes in the electric field at each point on the surface. Now see, if we have a Gaussian surface and we have charges inside as well as outside. So the flux producing by the charges will not be affected by the charges placed outside the Gaussian surface. So no variation in the flux, no matter whether the charge is inside or outside. But electric field will vary. How? We know that electric field flows from positive to negative. So suppose if this charge is positive and this charge is also positive, and if the electric field lines will go like this, then they will repel, they will get deflected from this point positive charge. And suppose if it is positive and this is negative, then it will attract it. It means in case of electric field, charge matters whether they are placed inside or outside, they will affect the electric field. So the 3 points that we saw is: number 1, electric flux is independent of the size and shape. Number 2, electric flux doesn't depend on the location of the charge. And number 3, that charge will not affect the flux, but it will affect the electric field. Now, before moving to its proof, we first need to understand the concept of solid angle for our ease. So, let's first understand it physically with an example. On our birthday, we cut the cake like this, and then we take out its piece and we get this. So, with the help of the fork, we cut the piece to eat. So, this angle, this solid angle, this whole part is the solid angle. This is the side angle view of the piece of the cake. So this angle is the solid angle. So diagrammatically we will show it as this, where this angle is the solid angle, which is represented by d omega. This is the r vector, this is the area ds, and the distance between the point 0 till the surface is the r. So it is given by d omega is equals to ds upon r square. You must be knowing the 7 fundamental units, in which the last one was of solid angle, having unit steradian. So unit of solid angle is steradian, and it is a dimensionless quantity. How? Because ds is the area, so its unit is the meter square, and r square, r is the distance, which is also meter, and square, so here m square, so it will give us a dimensionless quantity. Now let's consider 3 cases in it. So case 1, so suppose an elemental area vector ds makes an angle theta with the radial vector r vector. So the projection area perpendicular to the r vector is ds cos theta. This area was ds, now we have projected it with some angle. So now the area that we get is ds cos theta. So now the solid angle dq is the ratio of this projected area to the r square. So d omega is ds cos theta upon r square, and we can also write it as ds dot r cap upon r square. So first case depends on the angle, and we add the cos theta in the formula. So now in second case, area element, we have taken 3 different area elements, that are ds1, ds2 and ds3. All are subtended at the same solid angle at the point 0, because for them opening of the cone around its vertex O is same. From this point the opening is same, so these all areas will have the same angle d omega. Now case third, the solid angle subtended by the sphere at the center O is 4 pi, or we can say that the complete solid angle is 4 pi. So the value of the omega, it can be 4 pi or 0. So if the solid angle is at the internal point, then it will give the complete 4 pi angle. But if the solid angle is at the external point of the Gaussian surface, then it will give us the value 0. Now we are ready to do its proof. Let's consider a point charge q surrounded by the hypothetical closed surface S of an arbitrary shape. Then the electric flux, that is d phi, is equals to E dot ds, or we can write as E ds cos theta. Due to the point charge q, electric field at distance r is given by E is given by 1 upon 4 pi epsilon naught q upon r square r cap. So let's put this value of E in this equation. So we will get d phi is equals to, writing this equation and then putting the value of E. Since electric field is directed along the r cap, therefore the angle theta is the angle between the r and ds. Here area element ds is suspended at the solid angle d omega at the point charge q. So we know the value of the solid angle, that is d omega. It is equals to ds cos theta upon r square. So now you can see that ds cos theta r square, we are having this value here. So we can replace this term by d omega. So we will get d phi is equals to 1 upon 4 pi epsilon naught q d omega. We have replaced this value by the d omega. This is the flux. Now if we talk about the total flux through a closed surface, then it is given by, so total flux through S is, here we had taken the surface integral because we are talking about the closed surface, so we had taken the closed surface integral on d phi, which is the flux. It will give us closed surface integral 1 upon 4 pi epsilon naught q d omega. This constant value will write it outside, 4 pi epsilon naught q also and d omega. So phi is equals to q upon 4 pi epsilon naught omega. So this is the total flux through the closed surface S. Here the hypothetical surface S subtended at the total solid angle omega at the point of location of the charge q. So now putting the value of omega that we have calculated, 4 pi and 0. So we will get the value of phi as q upon epsilon naught and 0. So q upon epsilon naught if q lies inside the surface S, and 0 if q lies outside the surface S. How we get this? After putting the values of the omega, that are 4 pi and 0. Alright. Thus, in electrostatics, Gauss law is direct consequence of Coulomb's inverse square law. So this equation shows the Gauss law for this single point charge. Now, if there are number of charges as q1, q2 and so on till qn inside the closed surface, then their electric field will be E1, E2 till En respectively. So here we will apply principle of superposition. Then we will get, this is the simple formula of the flux, phi equals to E dot ds, putting the values. So we get E1 plus E2 and so on till En at the place of E and ds as simple. Then multiplying them, we will get E1 ds plus E2 ds and so on till En dot ds. So now from the Gauss law, that is E dot ds, it gives q upon epsilon naught. So we'll write phi as, so we can write these terms as q1 divided by epsilon naught, q2 divided by epsilon naught and so on till qn divided by epsilon naught. So we can write it in summation form as summation qi upon epsilon naught, where I can be 1 to n terms. So here we prove the Gauss law that phi is equals to summation of charges upon epsilon naught, or we can write it as q enclosed divided by epsilon naught. So this is Gauss law. What we saw under proof? First we had taken the flux, then the electric field, then we had placed this value of E in the formula of flux here, then we get this value. Then we had taken the solid angle d omega And we know that the value of d omega is ds cos theta upon r square. So here we replace this term by d omega. Then here we got the value of d phi, which is electric flux. Then we had taken the total electric flux on that Gaussian surface, and after surface integration we get q upon 4 pi epsilon naught omega, and after putting the values of the omega that are 4 pi and 0, we get the value of flux as q upon epsilon naught if the charge is inside the surface and 0 if q is outside the surface. Then if there are number of charges as q1 till qn, and respectively their electric fields as E1, E2 till En, then we'll write it as this. And at last we will get the charge in the summation form, and here comes phi is equals to q enclosed upon epsilon naught. So this proof was when charge lies inside the Gaussian surface. Now if the charge q lies outside the closed surface, then it will not contribute in the flux through the surface. We just saw here that when it lies outside, then it will give zero flux. So here we had taken charge outside the Gaussian surface S, where this is the first area and this is the second area. There are two areas where the cone is intercepting, that are ds1 and ds2. So these area elements are subtended at the same magnitude, that is d omega, at the point charge q. So this area vector is acting outwards, and here ds2 is acting outward in this direction. So the value of d omega ds dot r cap upon r square. So let's first talk about for the element ds1. So the solid angle d omega for ds1 would be here theta 1, that is this angle. So theta 1 is the obtuse angle. So d phi 1 would be equals to minus d phi 1. We will take this value as negative. Now ds2, here d omega 2 would be equals to positive d omega 2. Why? Because this angle is the acute angle. We had taken the values of the solid angle d omega 1 and d omega 2 for first area and second area, that is ds1 and ds2. And we had taken this angle negative because it is obtuse angle, and this is positive because it is an acute angle. So the flux contribution due to ds1 and ds2 are d phi 1 and d phi 2 respectively. So the net flux contribution due to both the area elements is given by d phi is equals to d phi 1 plus d phi 2. And we had taken d phi 1 as negative, so we will add a negative sign here. So they will cross each other and we will get 0. We are getting the net flux 0. If q is positive, then flux through ds1 is inward flux, whereas for ds2 it would be outward flux. But algebraic sum of their contribution to the net outward flux is 0. This holds for all the other elements. We can say that contribution of the outside charge in electric flux through the closed surface is 0, because the incoming flux is equals to the outgoing flux. This verifies the Gauss law. So now we are going to start differential form of Gauss law of electrostatics. So from Gauss theorem, E dot ds is equals to q enclosed upon epsilon naught. So now we are going to take a continuous charge distribution. Suppose we have this Gaussian surface and now the charges are truly spread over this region. So till now we were taking a point charge. Now what we are taking? We are taking many charges which are spread over this region. So it will now act as a volume. So we will use a volume element, that is rho. It is for volume. And for surface we use sigma, and for line charge distribution we use lambda. So here we are taking volume, so we will use rho. Now for continuous distribution of charge we have taken q enclosed, that is dq, and now we will replace this dq with the rho d tau. Here d tau is the volume element. which is containing dq amount of charge. So we can write it as rho equals to dq upon d tau, and here rho is the volume charge density. So we can write it as q enclosed is equals to limit tau rho d tau. Now the charge density, that is rho, it may vary within the volume. It may be more over here, less over here, or anything possible. So now we can replace the value of q enclosed from this value. So we can write it as E dot ds is equals to 1 upon epsilon naught line integral tau rho d tau. So this equation is the integral form of the Gauss law. Now moving further and applying Gauss divergence theorem, that is, we write E dot ds as del dot E d tau. This is divergence del dot. So in place of E dot ds we had replaced del dot E d tau and rest as it is. So now after integrating this, we will get del dot E is equals to rho upon epsilon naught. And this equation is differential form of Gauss law. This is also known as Maxwell's first equation in electromagnetism. And this is the Maxwell's first equation. Here, divergence of E at the position R, it depends on the volume charge density, that is rho, at the position R of that point. That is, divergence E is a function of the coordinates and it may vary from point to point. That's why this differential form of Gauss law is also known as point form and local differential equation. And we can represent that differential equation in Cartesian, spherical and cylindrical coordinates like this. These are the general form. And we know that divergence of E is equals to limit d tau tends to 0 closed line integral E dot ds upon d tau. So this is the outflow of the electric flux per unit volume at a given point in the limit of infinitesimal volume d tau. So we can write divergence of E as rho upon epsilon naught. Means electric flux per unit volume at a point is equals to the volume charge density rho at that point divided by the epsilon naught. So that's it. In this video we had gone through the Gauss law, then its 3 important points, then the solid angle, then its 3 cases, then we saw its proof, then we saw the differential form of the Gauss law, its integral form, differential form, Maxwell equation. Then we saw that how we write it in 3 coordinate system. So that's it by my side. Hope you found this video productive. Thanks for giving your time here. Take care.